Recall that determinant, we define it as, so suppose we have matrix A, then we define it as, we expand by, for instance, the first rule, okay, Aij times C1, A1G times C1G, okay, here C1G is the cofactor, okay, cofactor. The cofactor can be determined by the lower dimension case, okay, lower dimension case. So we define the determinant by induction, okay, define this by induction by dimension. So we give an example how to compute this by definition, okay, by definition. Okay, this agree with the 2x2 case, okay, 2x2 case, the determinant. Okay, now if you repeatedly use this definition of determinant, so what you finally get is expand everything, okay, every cofactor by determinant definition. So actually get determinant of A is, so we sum over all permutation, okay, sigma, okay, A1, sigma 1, A2, sigma 2, okay. Sigma 1, sigma 2, sigma n, they are just, numbers from 1 to n. Okay, so the sign of sigma is defined as 1 or negative 1 according to whether this permutation sigma is even or odd, okay, even or odd. And we show that it agrees with the definition for 2x2 case. Okay, and we determined the diagonal matrix, how the diagonal matrix the determinant should be, okay. All right, so this is what we did last time. And certain properties of determinant, remember? So we have the 10 properties, okay. Determinant identity is 1, okay, if we exchange 2 rules, then the determinant differ by -1. And if we do rule operations, for instance, we add, okay, if 2 rules are linearly independent, then the determinant is automatically 0. For determinant of matrix is the same thing as determinant of its transpose. So this property 4 tells us rule vector and column vector, rule and column, they are, on an equal footing in matrix, okay, in matrix. So number 5, adding a multiple of a rule to another rule does not change determinant, okay. So we can, so given a matrix, we can try to make it to be upper triangular, okay, try to make it to be upper triangular. Then upper triangular matrix is determinant that can be easily determined. So we can usually use the try to transform it into upper triangular form and then compute the determinant. And then what happens if we multiply a rule by lambda? Then determinant changes by also lambda. Now, if we multiply every entry, every rule by lambda, then the determinant differ by lambda to the power n. Okay, here n is the dimension. Okay, property 7. Determinant of product is product of determinant. Okay, product of the determinants of 2 matrices. So although matrix is in general not commutative, however, if we take determinant, then we are working in the real number. Okay, we are working in real number, and real number they are commutative. Okay, and the determinant of A inverse is inverse of A determinant. Okay, so this is what and then property 9, property 10, they are about diagonal matrix, or triangular matrix. Now we do several examples for determinants. Okay, let's see this example. Remember, as I explained, to compute by cofactor, it can be hard. It's not hard, it's just computationally expensive, okay? Too many operations. If you expand by the permutation formula, there will be too many terms. So for instance, this matrix A, Y, Y, Y. So we use the properties to find its determinant. 1, 2, 3. Okay. First of all, we can use the cofactor. So for instance, find determine A by cofactor. Okay, we expand by the first rule, for instance, by the first rule. Okay, so expand Y, the first rule. So let's look at the first rule. Let me color the first rule in red. Okay, the first rule. Okay, Y, Y, Y. Okay, so we expand. So it's a E11 is Y. So it's a E11. So this will be A11 times C11 plus A12 C12 plus A13 C13. Okay, A11, A12, A13, they are just 1. So it's the 1 times C11 plus 1 times C12 plus 1 times C13. Okay, now let's compute C11, C12, C13. Okay, now C11 is, we delete the first row and the first column. Okay, so the remaining thing is, don't forget the alternating factor, -1 to the power row plus column numbers, row number plus column number. And the remaining thing is deleting the first 1 entry, the first row, first column. Okay, so the remaining thing is 2, 2, 2, 3. Okay, so the 2 by 2 determinants we already know. Okay, so this is actually -1 to the power 2 is just 1. So this is 2 times 3 minus 2 times 2. So you get this is 6 minus 4. So this is the 2. So C11 is 2. So C12, we delete the second row and second, we deleted the first row, second column. Okay, first row, second column. So the second column, let's use color it in green. Okay, so the first, second row, color it in green. So we delete the red and the green. Okay, delete the red and the green. The red column, the green row. So the remaining thing will be 1, 2, 1, 3. Okay, the determinant. The determinant will be 1, 2, 1, 3. 1, 2, 1, 3. Okay, don't forget the alternating factor, -1 to the power row plus column. Row number is 1, column number is 2. Okay, so it's -1 to the power 3. So it's 1 times 3 minus 2 times 1. So this you got 3 minus 2, 1. But here is -1 factor, so it's -1. So C12 is -1. Now C13 is we delete the first row and the third column. So let's use another color. Let's use yellow. Okay, let's delete the yellow column. So the remaining yellow column, the red row. Okay, so what the remaining is 1, 2, 1, 2. So it's actually 0. Determined. So the remaining thing is 1, 2, 1, 2. Okay, 1, 2, 1, 2. So it's linearly independent. It's linearly dependent. Okay, identical vector. So the determinant is actually 1, 3. Determinant is, of course, is 0. Okay, so -1 to the power 4. You see 1 times 2 minus 2 times 1. So this, of course, is 0. No surprise. So the determinant of A is by what we just did. So it's C1 plus C11 plus C12 plus C13. Okay, so the determinant is because the first rule is 1, 1, 1. So those 3 A1, A2, A11, A12, A13, they are just 1. So the determinant of A will be C11 plus C12 plus C13. Expansion is the first rule. So you see, this is C13 is 0, C12 is -1, and C11 is 2. Okay, C11 is 2. C11 is 2. So this 2 minus 1 plus 0. So this is actually 1. Okay, we can also do this thing by rule operations. Try to get I try to find upper triangular matrix, transform A into upper triangular matrix. Okay, so we want the determinant of A still be 1. Okay. Okay, so A, we do rule operations that does not change determinant. Okay, so A is 1, 1, 1. So the fact is, if we add a rule to another rule, add a multiple of a rule to another rule, does not change determinant. Okay, so here we do rule operations. Rule operations. For instance, we do we want to try to cancel the lower, so the entries under the lower half of the main diagonal. So the main diagonal. So let me, the main diagonal in red is in red. So we want to try to make every entry below the red line, okay, the main diagonal to be 0, okay? So we use rule operations. So for instance, -1 multiple of first rule plus root 2 replace the root 2, i.e. we let root 2 add -1 multiple of root 1, and we let root 3 add multiple of negative root 1, okay, replace root 3. Now root 1 we just fix it. Root 1 we just fix root 1, no change. So root 1 is 1, 1, 1. Okay, root 2. Now root 2 subtract root 1. So 1 subtract 1, 0. 2 subtract 1 is 1. 2 subtract 1, 1. Root 3 subtract root 1. Okay, so 1 subtract 1, 0. 2 subtract 1, 1. 3 subtract 1, 2. Okay, now we do rule operation again. Fix the first rule. Now let root 3 add a multiple of rule -1 multiple of root 2. So root 3 minus root 2 subtract replace root 3. So root 1 and root 2 are fixed. 1, 1, 1, 0, 1, 1. Now root 3 subtract root 2, 0 subtract 0, 0. 1 subtract 1, 0. 2 subtract 1, 1. Okay. So root 1, root 2, root 3. Okay. Now you see this is upper triangular. Upper triangular. Here the determinant does not change. So you see determinant of A is actually equal to determinant of this, the matrix that's transformed. So this is the 1, 1, 1, 0, 1, 1, 0, 0, 1. Now it's upper triangular. So for upper triangular matrix, the determinant is the product of the main diagonal entries. So this will be 1. The main diagonal entry is, let's color it in red. Okay. The 3 1s on the red line. So it's a 1 times 1 times 1. So it's 1 times 1 times 1. So finally, this determinant A is again 1. You see, we compute the two methods. So we actually get the same result. Determinant A is 1. Okay. So this contribution, this is computation of determinant by either rule operations or determinant. Use definition by permutations. Okay, now for small matrix 3 by 3, this is, you can even compute by hand. Now for large matrix like 100 by 100, now if you use permutation, you need to compute 100 factorial terms. That will be a disaster. Okay, so in that situation, it may be easier. It's easier actually to try to manipulate with rule operations, so that then until you get upper triangular matrix. Okay, now we consider this matrix. This is a special matrix. Okay, this example. Vandermonde determinant. Okay, now you see the name named by one person. usually this means this thing is important. So here A is, so we just, for easier computation, we just do 3 by 3, okay, 3 by 3. Of course, you can find 4 by 4, n by n, find more determinant. So let A be this matrix, 1 A squared. So we stop at A squared. This is because 3 by 3. Now if it's for instance 5 by 5, you get A cube, A4, etc., etc. Okay. Now the second rule is you get a 1b squared, 1c squared. You see, we have certain symmetry. Okay. Now we want find a determinant of A. Okay. Remember, the determinant vanishes if the two rules are linearly dependent. Okay. Now, for instance, if A equal B or B equal C, then we have two identity rule vectors. Okay. Identical rule vectors. Then this means the determinant vanishes. Okay. The two rules will be linearly dependent. Okay. So you see, if first observation is if A equal to B or B equal to C, then we have, there are two rules. They are identical rule vectors, which means the rules are linearly dependent. Okay, this means determinant of A vanishes. Okay, determinant A vanishes. Now, for instance, we assume A, B, C, they are distinct. Okay, because we already know the easier situation, trivial situation. Now we assume A, B, C are pairwise distinct. So A not equal to B and B not equal to C and A not equal to C. Okay, pairwise distinct. Okay, now two methods. We can either explain it by definition, use permutation, explain it by rule vector, the first rule, and then transform it to 2 by 2 determinant. Okay, or here we use rule operations to transform A to be upper triangular matrix, and then we multiply the diagonal entries. Okay, so we get a determinant. Okay, so we use rule operations. Okay, use rule operations. So suppose A, let me write A here, the matrix A, 1A squared, 1B squared, 1C squared. Now we want to transform it to be upper triangular. So we do rule operations. So it's R1, R2, R3. Okay. Now what should we do? What rule operations should we do? Okay, let's first cancel the first entry, y1. Okay, y1. Okay, the first entry of root 2, the first entry of root 3. Okay, so you see the obvious operation should be add -1 multiple of R1 to root 2. So -1 R1 plus R2, so replace R2. And -1 multiple of root 1 add to R3. So -1 multiple of root 1 add to root 3, then replace root 3. Okay, so use this rule operation, then what we get is 1. So the first rule keep fixed. Now the second rule 0. Okay, now this B add, so we subtract the first rule, so it's A here. Now B squared, of course, subtract the first rule, A squared. So this rule 1, new rule 1, rule 2. Now root 1, negative root 1 plus root 3. So you get root 3 subset root 1. So it's the 1 subset 1, c subset a, c squared subset a. Okay. So this will be new root 1, new root 2, new root 3. Now you see, we have 0, 0 now. So we only need, now the main diagonal will be, look at the main diagonal. So the main diagonal 1 b minus a. So we have only 1 0 entry below the diagonal, below the main diagonal. Okay. So it's the second entry in R3. Okay. C minus a, C minus a. So we will try to cancel that C minus a in R3. Okay. Remember, we assume that ABC, they are pairwise distinct. Then we do the following operation. We do the following operation. So we do this operation. Use this multiple b minus a, c minus a. This thing, if you multiply this root 2, then b minus a will becomes negative c minus a. So it cancels c minus a. Okay. So this is the right multiple that we do the cancellation. Do this operation. This multiple of R2 added to R3 and then replace R3. Okay. So R1 and R2, they are keep fixed. So then what we get is 1a squared. Now 0 b minus a, so root 1 and root 2 fixed. Okay, b squared minus a squared. Now this becomes 0. Now because we use the right multiple of R2, so this entry c minus a vanishes now. Is now the remaining thing will be now multiply a multiple of R2. So the R2 will be, you see, it's a negative c minus a, b minus a. Multiply R2. R2, the entry, the 2, 3 entry of 2, 3 entry, second row, third column will be b squared minus a. Okay. Now add it to R3. So add c squared minus a squared. So this is the c squared minus a squared is the original entry in R3. Okay. So the determinant will be the 3 terms, product of the 3 diagonal entries. Okay. So determinant of A. Now here we already have upper triangular matrix. Okay. Upper triangular matrix. So we find determinant of A will be, okay, the terms. So we have 1 times b minus a. Now the last term, if you clear denominator, rearrange. So the last term b squared minus a, b squared minus a squared. So use difference of 2 perfect square formula. So if you check, so c minus a, b minus a times, now b squared minus a squared will be b minus a, b plus a. Okay, plus c minus a, c plus a. Difference of 2 perfect squares. So this you cancel denominator. So this will be negative c minus a, b minus a, plus c minus a, c plus a. Use common factor c minus a. So this will be negative c. It's c minus a, c minus a. Then this will be negative b, negative a, plus c plus a. So this will be, you see, so this will be c minus a. Now minus a plus a cancel out. So this you get a c minus b. Okay. So you finally get the 3, 3 entry, a 3, 3 entry. Third column, third row will be c minus a, c minus b. Okay. C minus a, c minus b. So in this case, so we got the determinant of a. You see, it's so 1 just 1. So this you got a b minus a, c minus b, c minus a. Okay. You see, if c equal to a or c equal to b, or A equal to C, etc., etc. If one of the three letters ABC are equal, okay. If two of the letters are equal, then you see we get a term 0. Then the determinant vanishes, okay. So the determinant will be exactly this form, okay, this form. B minus A, C minus B, C minus A. So this 3x3 case, okay, 3x3 case. Now here it's really confusing to get to remember the orders, okay. It's hard to remember the orders. Okay, which is first, which is second, etc., etc. So it's easier to remember the determinant squared, okay. So if you have n by n matrices, okay, n by n, so this you get y x y da 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 x y to the power n. Sorry, n minus 1. I mean, let's use n minus 1. X1 to the power n minus 1. So this is n by n. So we start with power 0. So y x2 da 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 da. So this is x2 n minus 1. Then you have y xn da 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 xn to the power n minus 1. Then this determinant. So this is a to be this thing. Okay. Then what you get is determinant of a is let's use determinant squared. So this will be xi minus xj squared. I not equal to I is from 1 to n. Ij is from 1 to n. Now, of course, I is not equal to j. Okay, so you get the thing. So this is the Riemann determinant. A famous example. Okay, homework for this section. Okay, section 5.1, we do number 1, number 8, part A, number 13, number 22, and number 30. Homeworks for section 5.2. Let's do number 1, number 12, number 16, number 19. Okay. Now we start Cramer's rule. Next section. Cramer's rule. Okay. Now recall that we define the minor of a matrix. So let's remember, let C be the matrix of minors. Let C be the matrix. So last time we defined minor of a matrix, the matrix of minors of a matrix A. Okay, i.e., if A is n by n, so A is in A here is in a matrix n by n matrix. Okay. Then the Cij minor, Ij's minor will be -1 to the power I plus j. Okay. Root number plus column number times Mij. Okay, Mij is, so here Cij is the cofactor. Did I use the wrong definition? Okay, sorry, I mean the cofactor. Sorry, I mean the matrix of cofactors. So Cij is a cofactor. Cofactors. Matrix of cofactors. So Mij is the minor. Okay, Mij is the IGS minor. Mij is the IGS minor. Remember, a minor of a matrix is obtained by deleting the I through and J column, and then take the determinant. Okay, take the determinant. Okay. Okay. Now we do this. We check this following. Cramer's rule says we can find the inverse of a matrix explicitly by these cofactors. Okay, by a matrix of cofactors. So we show that. Now we show that we have explicit inverse A times CT transpose. Okay, the matrix cofactor matrix transpose is actually determinant of this matrix A times identity matrix. Remember, determinant of A is a number. Now, if determinant of A is non-zero, so we can divide. Do the scalar division or scalar multiplication. So then you got A inverse. So we got A times determinant of A. So this number. So we divide by determinant of A, and then put it to CT, this matrix, CT. Okay, this will be identity matrix. So this means we have a possible choice for the inverse. So actually, we remember we have A inverse. A times A inverse is identity. So actually, we can determine A inverse. Then A inverse is nothing else. It's determinant CT over determinant of A. Okay. Okay, this is very easy to show. This is not difficult to show. Okay. So if we write explicitly, if we write proof, if we write A as explicitly A1 A1n. So this is the first rule. Now we have nth rule ANN. Okay, so this is the matrix in entry form. Okay, so CT. Remember, determinant of A. Determinant of A is you use expansion by any rule. Aij, Cij. Okay, Cij. I is fixed. J is from 1 to n. Okay, we fix I for some fixed I for I for some I fixed for I be for some I in 1, 2, 3 all the way to n for any I. Okay, as long as it's in 1, 2, 3 all the way to n. Okay, so this expansion using any rule. Okay, so you check A times the vector A times the matrix CT. Use product. Okay, use product formula for the diagonal entry II is this will be the ij entry of A times let's use key. Did I use J? Oh yeah, I use J. Okay, CT Ji and sum over the J. Okay, sum over J. J from 1 to n. Okay, so this is matrix product using the definition of matrix product. So the diagonal entry II entry will be Aij times CT Ji sum over J. Okay, sum over J. Now CT Ij Ji they just transpose flip row and column numbers. Okay, so this will be G is from 1 to n. Aij times Cij. Okay, C and CT, their Ij entry flip rule and flip rule is column. Okay, so G, so we cancel the T transpose. We can flip I with G, flip G number rule number with column number. Okay, and this is our definition of a determinant. Okay, this is actually our definition of determinant. Okay, this is our definition of determinant. Okay, where we use the definition, look at the red circle, the red circle, we use the red circle, then we get this. Okay. Okay. Now a determinant means this is okay. If G is not equal to I, so the off diagonal entries of this matrix A times CT. Let's look at the off diagonal terms. For G not equal to I, then let's look at this A times CT. A times CT, IJ. Then this you get, what you get is, this you get AIK CT KJ. Okay, so we sum over G is sum over K. Sum over K. Okay. Now CT KJ. So we switch root number with column number and cancel the transpose. It's AIK CKJ. Here G is not equal to I. G is different from different than I. Okay. So we sum over K. Okay. Now this will be this determinant. Okay. Now remember, if we expand this thing, so this will be the determinant for this matrix. This will be determinant of B, where B is this matrix. Where B is this matrix. B is, so we A11 dot 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 dot. So we obtain B is obtained by replacing the Jth rule of A by the Ith rule of A. So A1n. So we have 1, 2, da 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 da. We have I, we have J, for instance here. Finally we get n. So the Ith rule, we get the Ith rule. Now the Jth rule is A, again, the Jth rule for A will be AJ1, AJ2, AJn, okay? Now we replace the Jth rule by the Ith rule of A, AI1, AIn. Now this, etc., etc. Finally, we get AN1, ANN. So here B is obtained. B is obtained by replacing the Jth rule of A by the Ith rule of A. Now here, first of all, we claim determinant B is 0. Determinant B is 0. Okay, why? Why this determinant B should be 0? Determinant B should be 0. There are two reasons. Okay, first of all, so we have two rule vectors. They are identical. We have two identical rule vectors. Now, which means they cannot span Rn. Okay, the volume should be 0. So this is the one geometric reason why determinant B should vanish. Another reason is, remember when we switch the two rules of a matrix, okay, the determinant differ by a sign -1. Okay, so you see the determinant B. If you switch the IJ rule of B, it does not change. Okay, the B, determinant B does not change. So this still is the determinant C, determinant of B transpose, determinant of B switch IJ rule. So it's still again determinant B. Okay, i.e. the determinant B equal negative determinant of B. Okay, so this reason, this also you solve a number equal to negative this number. So you get this number is 0. Okay, either way you get determinant B is 0. So finally determinant B we get this is 0. i.e., the matrix A times CT, all diagonal terms, all vanishes. Okay, so we finally get A times CT. Ij is 0 if I not equal to j. Okay, so i.e., all of diagonal terms, of non-diagonal terms, all of diagonal terms vanish. So the diagonal terms, they are determinant of A. So this matrix, so this A times C CT will look like this matrix. Okay, so we have this determinant A is a number, determinant A, etc., so determinant of A, and a bounce of 0 here. Now if you divide, so this is the number determinant of A times identity matrix y, y, y. Okay, so you finally, if determinant of A is non-zero, okay, so you can divide. If determinant of A is non-zero, so we can divide it. Then we can divide. Okay, divide. So you gotta divide, and then put it here. Put it determinant A here. CT. Okay. Scalar you can put it anywhere. Okay. The scalar you can put it anywhere. So this will be the identity matrix. Y, y, y. So this simply just identity matrix. So you actually, then we find the inverse. Okay, then we find the inverse. So which means, remember, A is invertible. Okay, so A inverse. So we find A inverse to be determinant y over determinant of A CT. Okay, y over determinant of A. Okay, where Cij is -1 to the I plus j Mij is a ij cofactor. Okay, so this Cramer's rule tells us how we can find A inverse explicitly. Okay, explicitly if we have matrix. Remark. If A is large, now this, we need to compute a lot of cofactors. This turns out to be really expensive computationally. Cramer's rule is computationally expensive for large n. Cramer's rule is computationally expensive. A large number of operations for large n. Okay, for large n. Okay. We have another algorithm. Remember, Gauss-Jordan. Okay, Gauss-Jordan. Use linear elimination. Okay, use linear elimination. That actually is not so computationally expensive than Cramer's rule, because Cramer's rule we need to evaluate so many determinant minors. Okay. Okay, let's see some examples. Okay, A is A, B, C, D. Now we do some lower dimension example, 2 by 2. Okay. Then we have determinant of A. Everyone know. Okay. So it's AD subset BC. Okay. AD subset BC. Now let's find the minor. Okay. The minor. Okay. So the minor M11 of matrix A. So we delete the first row and the first column. Okay, first row, first column. So the first row, first column. Let's use the red. If you delete the first row, the first column, then the remaining thing will be D. Okay, so M11 will be D. M1 will be delete. Now M22, let's use another color. M22. So we delete the first second column, second row. Let's use green. So if you delete the first row, second row, second column, then you see this is the A. Okay, the remaining thing is A. Okay, similarly, M12. What is M12? M12. Okay, we delete the first row, second column. Okay, first row, second column. So M12 will be C. Okay, so if you A, B, C, D. Okay, if you delete, let's use another color. Let's see, let's use yellow. Okay, if we delete the first row, second column. Okay, delete the first row, second column, then the remaining thing will be C. Okay, the remaining thing will be C. Let's use yellow. Okay. Okay, now M21. Okay, M21. This will be so let's see A, B, C, D. So we use another color. Let's see, use purple. Okay, we delete. So 2-1. So second row, first column. So second row, CD. First column, AC. So the remaining thing will be B. Okay, B. Now we need to consider IG. Consider cofactor. When we consider cofactor, we should consider the alternating factor, -1 to the power I plus J. Okay. So C. Let's consider. Remember, we need to consider the cofactor. Okay, consider the alternating factor, root number plus column number. So 1 column, we get a root number plus column number 2. So this is actually positive one. So it's actually positive D. 2, you know, it's A. 2 plus 2 is 4. 1, 2, and 2, 1, they are 3. Okay, all. So it's actually negative. So here, C, negative B. And we need it. Remember, A inverse is determinant A times C transpose. Okay, determinant A, 1/determinant A times C transpose. So we need to transpose that matrix C. Okay, so C transpose. So we flip with respect to the main diagonal. Okay, flip, switch rule with flip with the main diagonal. So the main diagonal does not change. But then so C switch with B. Okay, C switch with B. So finally we get CT. CT is, okay, let's use this color. So CT will be DA keep fixed. Negative C, negative B, they switch with each other. Okay, so A inverse will be determinant A. Remember, determinant A is AD minus BC. Now CT will be DA negative B, negative C. Then we're done. Okay, then we're done. Okay, let's see one example. Let A be this matrix. Let's see, this is a 1, 2, 3, 5. Okay. So we use our old Jordan elimination to find A inverse and compare with Cramer's rule. Okay, compare with Cramer's rule. Now Jordan elimination, remember Jordan elimination. So we use an augmented matrix AI. Okay, so this will be 1, 2, 3, 5. Here we have 1, 1, 0, 0. Okay, we transform the left side A into I, and then I will transform into A inverse. Okay, so we use rule operations. So we transform the thing, use R1, R2. Okay, so R1, -3 R1 plus R2, replace to R2. So this will be 1, 2, 1, 0, add -3 multiple of R1. So this will be 0, 2, add -1. So it's -3 multiple of root 1. This is 1. Okay, now we divide root 2 by, did I get a mistake? Wait a second, this should be, this is wrong. So this should be -1 here. Okay. Okay, then multiply, so it's R1, R2. Multiply root R2 by -1. So 1, 2, 1, 0, 0, 1, -1, 3 here. Okay, then R1, R2. Then we cancel the 2 on the first row, second column. So we let -2 R2 add to R1, replace the R1. So you see this, we get 1, 0. So the second row keep fixed, 3, -1. Then 2 add multiple or -2 multiple of the root 2, this gets 0. Then this we get 1 plus -6 is -5. And here this we should add 2, okay? -2 multiple of R2, so this is actually -2 times -1, so we get 2. 2 plus 0, we get 2. Okay, so this is I A inverse. So you finally find A inverse by Jordan, Gauss-Jordan, eliminate Jordan, Gauss-Jordan. So it tells us A is 5, 2, 5, 2. This is, so it's -5, 2, 3, -1. Okay, remember A is 1, 2, 3, 5. Okay. Okay, now we use Cramer's rule. If you use Cramer's rule, you said we have, remember Cramer's rule. So Cramer's rule tells us ABCD. If A is ABCD, then A inverse. Cramer's rule tells us its determinant of A is AD minus BC. So here this is DA. Oops. And this is -B, -C. Okay, so here you see this is ABCD. Okay, so A is ABCD. You can find its value. So AD minus BC. So this will be 1 times 5 minus 2 times 3. So this will be -1. Okay, so this will be 1 over -1. Now D is 5. So here 5. B is 2. So -B is -2. C is 3. So it's negative. C is -3. A is 1. Okay, C is 3. So it's -3. A is 1. Okay, if you multiply -1 inside, so you finally get A inverse. Okay, you finally get A inverse. Use Cramer's rule. Finally we get multiply -1 to every entry. So you get -5, -2, so we get a +2. -3, we get a 3. -1, so we get -1. So you see, this is exactly identical with what we get using Gauss elimination. Gauss-Cramer, Gauss-Jordan elimination. You see, we get the same. Okay, we use Cramer's rule and we use Gauss-Jordan elimination. So we get the same A inverse. Okay, so we get the same A inverse. look at the two red circles. You see we get the same answer for Gauss-Jordan elimination and Cramer's rule. Okay, it makes sense. It makes sense. Okay, the right solution, the right result. Okay, here the result should be unique. If we find two distinct results, then at least one of them should be wrong. Okay, so this is this example how we use Cramer's rule to find inverse of a matrix. Or you can check this A multiply A inverse, you get identity matrix. Okay, use this is very easy to check. Okay, so for instance, let's maybe do one example. So let's just that's easy to check. So A times A inverse. This is 1, 2, 3, 5 multiplied by -5, 2, 3, -1. You can check. Okay, the first rule, 1, 1. First rule times first column. Okay, so you get a -5 plus first rule, -5. First rule times the first column plus 2 times 3. Okay, which is 1. A1, 2. The first rule times the second column. A1 times 2 plus 2 times -1. So this is of course 0. Now A1, 2. This is the 1, 2. Sorry, 2, 1, 2, 1. Then second rule times first column. 3 times -5 plus 5 times 3. This is also 0. And then A2, 2, 2, 2 is second column times second rule times second column. 3 times 2 plus 5 times -1. You see this, you get -5 plus 6, you get a 1. 6 minus 5, you get a 1. The other you easily check, you get a 0, 0. So this is identity matrix. Okay. If you can also check A inverse times A, you also get an identity matrix. Okay. Then we're done for this example. Okay, Cramer's rule tells us how to solve A inverse. Okay, how to solve A inverse. If you know, from Cramer's rule, we also know the determinant is non-zero. Then the A is invertible. So easy corollary of Cramer's rule is this thing. Okay, a theorem. So you see, from Cramer's rule, when we find the inverse of a matrix, the only thing that we need to do is we need to divide determinant of A. So this is only possible if determinant A is non-zero. We can only divide a non-zero number. So A inverse exists, i.e. A is invertible. This is the equivalent to determinant A is non-zero. Determinant of A non-zero. Okay. Okay. Okay, we can also use this theorem to check whether if n vectors in Rn, whether they are linearly independent or not. Okay. Put them in matrix form and compute the determinant of this matrix. If the determinant of this matrix is non-zero, then we know they are linearly independent. Okay. Okay. Once we have A inverse, we can solve certain linear system. Okay. So suppose we have linear system such that A inverse exists, i.e. A is invertible. So now the next thing is linear system. Given a linear system. Now we have A inverse by Cramer's rule. So we can use Cramer's rule actually to solve linear system. A times X equal to the vector B. So here X and B, they are column vectors. Where we assume with that A being invertible, where A is invertible. Okay, where A is invertible. invertible. Then we have A inverse. Then we can actually do the A inverse. So if we do A inverse AX, then we get A inverse of B. Okay, so A inverse times A gives us identity. Okay, identity times X gives us X. So X is A inverse times B. Okay, A inverse times B. Now this can be written down explicitly. Okay, this can be done explicitly. So if we are dealing with n by n, so suppose X is n vector, X vector x1 xn. Okay, B is b1 bn. Okay, now A is of course A is the matrix E11 A1n all the way to AN1 ANN. So this is n by n matrix. Okay. Now we already know A inverse. Okay, so X is, we find a solution. X is A inverse times the vector B. Now A inverse is, okay, let's find xi. Okay, so what is xi? Xi is, so if you write down, so this is the vector A inverse B. This vector, this is the column vector. Okay, column vector. Column vector, it's a I through first column. That's only one column because it's column vector. I through column, first column. Okay, so this will be this A inverse I times J times BG1. Okay, BG1 sum over J. BG1 is just because B is a column vector. BG1 just J through first column, so it's just BG. Okay, it's just BG. So this will be, if you write down what this A inverse is. So A inverse, remember A inverse is 1 over determinant of A CT. Okay, CT. So A inverse IJ is 1 over determinant of A CT IJ. So A inverse IJ will be determinant 1 over determinant of A CT IJ. Now transpose, we switch root number with column number. So we cancel T, and then so we get this is CGI. Okay, CGI times BG. Okay. Now this will be this matrix. Okay, so sum over J. J is from 1 to n. What we get is this 1 over, if you factor the determinant A, so this will be J to be 1 to n. It's a Cij Bj. If you, now this will be this matrix. Determinant of this matrix. So this we write it as this 1 over determinant A times determinant B. Where this B is this matrix, we replace the ith column of A by the vector B. Okay, so we replace, so B is this matrix. A11 So this is the ith column. So we replace the ith column of A by B1, B2, Bn. Okay, so everything keep it fixed. So we just replace the ith column of A, of the matrix A, by the vector B. Okay, if you expand by column, then you get the form. Then you can find determinant B, which is actually Cij times Bj. Okay, so Bi. I will give you one example in a moment. Okay, where the matrix B, where Bi is obtained by replacing the ith column of A by the vector B. Replacing the ith column of A by the vector of B. Okay. Now let's see one example. How the Cramer's rule. How we apply Cramer's rule to solve linear equations. Okay. Example. How we use Cramer's rule to solve linear system. Okay. X plus 3, 2y is 11. Now 3x plus 5y is 29. Okay. Now this, of course, two equations, two variables, this can be easily solved. Okay. This example we can easily solve use our old method. So looks like trivial, but we just use this idea to show this how this Cramer's rule works. Okay, how Cramer's rule works by this method. So this you write it as this matrix A. Write down the coefficients matrix. Okay, so it's 1, 2, 3, 5. Now the vector B is 11, 29. Okay, so you write the equation as Ax. So here the vector x is xy. Okay, so you write the linear equations as Ax equals B. Okay, so write in the matrix form. Now we use the Cramer's rule. Okay, Cramer's rule tells us that xi is so for instance b1, how do we get b1? We replace the first rule by the vector b, so the vector b is 11, 29. So it's 11, 29. The second keep fixed. So you see here determinant A is easy. Determinant A is 1 times 5 minus 2 times 3, which is -1. Okay, -1. Okay, so then this says x1 is determinant of b1 over determinant of A. Now determinant of b1 you can easily check. It's 11 times 5 minus 2 times 29. Determinant of A is -1. So you see this will be 55 minus 58 over -1. And this will be -3 over -1. So this is 3. So x1 is 3. x2 is just y. Okay, x2 is determinant of b2 over determinant of A. So determinant of b2 is replace the second rule of A. Remember A is 1, 2, 3, 5. The second rule, replace second rule. 1, 3, the first rule fixed. Second rule, replace second rule by the vector of B. Then you check determinant of B2. Determinant of B2 will be you know, 2 by 2 determinant. So 1 times 29 minus 11 times 3. So you get 29 minus 33. So this you get -4. And then you find x2. Okay, x2 is determinant of b2 minus over determinant of a. Determinant of a. So you get determinant b2 is -4. Determinant of a is -1. So you get this is the 4. So the solution x1, x2 is 3, 4. So you get xy, okay, or x1, x2 is 3, 4. Okay, so we get the solution is 3, 4. Now you can easily check 3, 4 satisfies this equation. Okay, you plug in 3, 4 to the original equation. Okay, this can be easily checked. Okay, x plus 2y, 3 plus 2 times 4, 3 plus 8, 11. Okay, now x is 4, 3x 12. Okay, y is 4, 2 or 5, y is 20. Okay, 20. So 3x, x is 3, 3 times 3, 9. 29 plus 20, you get 29, okay? So this indeed, 3, 4 is the solution to this thing, okay? So i.e. to summarize, okay, if we have a linear system n by n, okay, n variable, n equations, where the coefficient matrix are invertible, then we can solve by Cramer's rule, okay? The xi is we replace the ith column of the matrix, coefficient matrix, by the vector b, okay, by the column vector b, okay? So xi is determinant bi over determinant of a, okay? So this is how Cramer's rule solve linear system, okay? Okay. Okay, another thing that maybe let me mention a little bit another thing. Okay. Remember A inverse is 1 over determinant of A times CT. Okay, now if you take determinant, now remember determinant of lambda A. Because this probably determinant lambda A is lambda to the power n, determinant of A. Okay, so and also determinant of A inverse is inverse of determinant. Okay, now if you take determinant to the equation in red, okay, in red, let me plot the thing in red. So Cramer's rule tells us that fact, okay? Cramer's rule tells that the red, we can use the red, okay? Red circle to compute the A inverse. Now, the two matrix should be equal. The two matrix should be equal. Then we can take a determinant of this matrix, okay? If we take determinant, apply determinant operation to Cramer's rule. Then we get the left side determinant of A inverse. The right side we get determinant of the thing. So here 1 over determinant of A is a lambda, okay? That is, okay, 1 over determinant of A is a scalar, okay? Determinant of 1 over determinant of A times CT. So here, let me use a colored thing, the green. So the green part, 1 over determinant A equal to lambda. We take that thing to be number lambda, okay? So according to the multiplication, the rule when we take a determinant for multiplication, then what we get is lambda to the power n, okay? Lambda to the power n. Here lambda is 1 over determinant of A to the power n times determinant of CT. Remember, determinant of transpose of a matrix equals determinant of a matrix itself. So this is the 1 over determinant of A to the power n times determinant of CT, C or CT, the same. So this left side is 1 determinant of A inverse is the inverse of determinant. So this is 1 over determinant A. Okay, so if you rearrange this, so you actually get determinant of C. Okay, the cofactor matrix, determinant of the cofactor matrix is determinant of A to the power n minus 1, where C, this A is n by n matrix. Okay. Homework for this section. Okay. Homework for this section. Let's do number 1, number 6, number 17, number 24, number 38, part A on the textbook. Okay. Okay. Now let's talk about the next chapter, eigenvalues. Eigenvalues. Okay, next chapter, chapter 6, is about eigenvalues and eigenvectors. Okay. Chapter 6. Eigenvalues and eigenvectors. And eigenvectors. Okay, some idea. The idea is we want to find invariant of certain operations. Idea. We want certain things that has nice property. Okay, we want to find invariant under certain operations. Certain operations. So this has many applications. Let me give you one example. The example. This example. If you go to go gambling. Okay. If you go to casino, then go gambling, and you should know this. Force shuffles. First shuffles. What is first shuffles? This is, you know, okay, this is the operation that you try to shuffle a deck of cards. Okay, it looks like the deck of cards is shuffled to the random order. Okay, into random order. However, under complicated operations, okay, that people know that under certain complicated operations, it looked like a random shuffle, but it turns out the order of entire deck is fixed. Okay, doesn't change. Okay, if I give you a deck of cards, you under certain complicated shuffle, then it turns out the order is the same thing as the initial. Okay, is the same thing as initial deck. Okay, so this is called force shuffles. Okay, so here the invariant is the operation is the shuffle. Okay, the shuffle. You do this operation, do the shuffle, and the invariant is the order of the entire deck. Okay, here the order of the entire deck is fixed. Okay. Suppose you have a certain good order, of a deck of card, such that you can get 3A or 3K, okay, KKK or 3AAA, such good card to certain people with this fixed order. Okay, so under this shuffle, for shuffle, you can keep this order such that many people use this thing cheating in the casino. Okay, cheat. Okay, so this is one example. That we want to know invariant of certain operations. Okay, so there are many examples. For instance, another example. If you play these dice games. Now, if you want, for instance, let's just make it simple. If you want play certain number, if you want play dice, if you want number 5, how do you get number 5 with a good probability? Okay, how do you get 5 with a good probability? Okay, of course you can control the dice by some cheating thing. Now here we just use the physics rules. Okay, for instance, if you add a certain spin to the dice, okay, when you play the dice, you add a certain spin, okay, then the dice is more likely to remain the same as its initial position, because once you have a certain spin, it does not, it's hard to change direction. Okay, change direction. So dice gambling. So you can add a certain spin to add. You use spin. Okay, you add a spin to your dice. To the dice. When you play this dice, throw out the dice with certain spin. Okay, then the dice is more likely to keep its initial direction. Okay, because of the spin. Then you more likely you start with 5, and then you use some spin. Then it's more likely that you finally the dice will end up with 5 point. Okay, 0.5. Okay, then okay, then the dice is more likely to remain the same, remain its initial position. Initial position. Okay. I.e. invariant, either invariant. Now for matrix, okay, if you view matrix as a machine, okay, if you view matrix as a machine, you plug in a vector, okay, then the output is also a vector. So given a matrix, square matrix, giving a square matrix A, you can view this matrix A as an operation. Matrix A, so it's n by n. So then A defines a rule that you plug in a vector, then you output A times this vector. Okay, so then A defines a rule. A defines, so we call it an action. A defines an action on vectors. Okay, action on n-dimensional vectors. I.e., you plug in an n-dimensional column vector V. Under this rule, we can output A times the vector V. Okay. Okay. Now we want to find the invariant of this operation E. Now, which vector that is, we plug in V, okay, under this machine, under this operation, we still get a V, okay. Now it turns out this is too strong usually. Okay, this is too strong. Okay, usually if you plug in V, you cannot. It's possible that we can never get A. Okay, so it's too strong. This is because so we may not have a solution if we want the same thing as V. However, we can make it less stronger. So we can assume just as long as we fix the direction, i.e. the output is the same in the same direction as the input. Okay, i.e. So if we want to fix, so this condition is too strong. The condition AV equal to V sometimes is too strong. Is too strong. Too strong for meaningful vector. Okay, for non-zero vector. Okay, so of course this always has trivial solution. You plug in 0, you get a 0. Okay, that's boring. That's boring solution. Okay, that's boring. V is non-zero. V is non-zero. So we assume this V is non-zero. So this is too strong. So we don't have interesting thing. So and we may so this is too strong, and we of course we may not have meaningful solution. We may not have meaningful or non-trivial solution. So we just make it less stronger. So we may do this. AV equal to lambda V. Okay, this means input V, output lambda V. So it's parallel. The output is parallel with V. Okay, parallel. So we plug in V, output a multiple of V, i.e. the operation, the action, or the operation. The operation skews the vector by lambda. Okay, multiply the vector lambda by a multiple. Skew the vector V by a number lambda. Okay. So now this is a meaningful operation. Now we give a definition. So this we give a definition. So this definition. If so, here A is A by N. If AV, the output is lambda V for certain non-zero vector V for some. So for some non-zero, if you plug in 0, you can. This is trivial non-zero vector V, and here lambda is some scalar, and some scalar lambda. Then we call this V to be eigenvector. Then we see V is an eigenvector. Eigenvector of A. Okay, with eigenvalue lambda. So lambda is called eigenvalue with eigenvalue lambda. Okay, value lambda. Okay, let's see some examples. Example. Now let's first see one really old example. The magic square. Magic square. This is a really old example. Let me show you a picture. Let me see a picture of a magic square. Okay, this is the magic square. Let me show you the picture. New share. Okay. Okay, so this is the magic square. Okay, magic square. It's really old. Okay, so you see the numbers. You rearrange number 1 to 9 such that the column, row, and diagonal sum to the same number. Okay. This number you can easily calculate. Okay, should be 15. Okay, now let's go back to our original. Okay, so the magic square, or you call it in Chinese 罗苏, if you can read Chinese. Okay, the matrix A is this 4, 9, 2, 3, 5, 7, 8, 1, 6. Okay, we want to find eigenvalue and eigenvector. Find eigenvalue and eigenvector. Find one eigenvalue. Now, first of all, remember this this magic square subset is row and column sum to the same number. Okay, so if you choose this vector v to be 1, 1, 1, 1, 1, 1. Now a times v, this will sum over. So AV, how do you get an AV? AV is this 4, 4, 9, 2, 3, 5, 7, 8, 1, 6 times 1, 1, 1. Okay, so this means we sum. So this you get, we sum 4 plus 9 plus 2, 3 plus 5 plus 7. Okay, and 8 plus 1 plus 6. Or this is a rule picture. This is a rule picture. Or you use the column picture. Okay, you can also use the column picture. So this you get 15, 15, 15. Okay, so this is 15. You can also use the rule column picture, add the 3 columns. Add the 3 columns of the magic square. So you get 15. 1, 1, 1. 1, 1, 1. Okay, so you see this. So we have an eigenvalue and eigenvector. So you see 15. So A has an eigenvalue. Eigenvalue. Now this eigen comes from German word, means own or self. Okay, eigenvalue has an eigenvalue 15, and eigenvector 1, 1, 1. Okay, so the sum, you see the sum of the row and column, they are 15. So this 15 in some sense tells the sum of the column and row. So eigenvalue. So this is one example, old example of eigenvalue and eigenvector. Okay, now another, maybe everyone like it. Okay, is this matrix. Let me another example. Now you have this example. That's the famous. Everyone, maybe some of you maybe played this. Sudoku matrix. Okay, now this matrix, maybe you see a picture. Let me find a picture for that. Okay, you see, let me show the picture. Okay, let me share this to you. Okay, let me show this picture to you. Okay, share this. Okay. You see the matrix. You see the numbers. We rearrange the numbers such that every row and a column, they are just just permutation of 1, 2, 3, 4, all the way to 9. Okay. Every row and a column contains the number 1 all the way to 9. Okay, exactly ones. Okay. Okay, now if we have a such matrix, now it's, I would of course not write this matrix. We have too many numbers. Okay, too many numbers. So if we just assume A is such a matrix. Okay, A is such a matrix such that every row and every column contains exactly the number 1, 2, all the way to 9 exactly one time. Then you have like the magic square. Okay, you can view this as a large magic square. Then it has eigenvector 1, 1, 1, 1, 1. Okay, you have exactly 9 ones. Okay, 9 ones, 9 ones. Okay, then if you multiply, this is an eigenvector. Okay, V is a thing. So you get A times V, the sum of every rule, the sum of every rule. Then you get a 1 plus 2, plus 9. For every entry. So this actually, every entry you get 1, 1, 1. So you get a 1, 1, 1, 1. So this is actually this multiple of a V. So this matrix A has eigenvector 1, 1, 1, 1, okay, 9 ones. And with eigenvector 1, 2 plus 9, okay. So this is the sum 1 to 9. You get okay, sum 1 to 9. So you get 10 times 9 over 2. So you get a 45. Okay, you get a 45. It's 45V. So here, this Sudoku matrix, you can view it as a giant magic square. This eigenvalue 45. Okay. So these are two examples of eigenvalue and eigenvectors. Okay, the next question is, how do we find eigenvalues? How do we find eigenvectors of a matrix? Okay, given a matrix, how do we find its eigenvalue and eigenvectors? Question. Given a matrix, now of course, given a square matrix, how do we find, question, how to find its eigenvectors and eigenvalues, eigenvalues and eigenvectors. Okay. Okay. Now we use the definition. Let's see, go back to the definition. Okay. So suppose we have matrix A. Now suppose we have A, we have eigenvector A times V equals lambda V. V is non-zero. V is non-zero. Okay, then, so if we have this, then if we write in this manner, AV minus lambda V, this is, if we write in this form, A minus lambda times I times V, okay, equal to 0. Then you see V is in the null space. V is the non-zero vector V is in the null space. Is in the null space. Null space of the matrix A minus lambda I. Then this means, so this means the matrix A minus lambda I has some non-trivial null space. Then this means the matrix is singular. Okay, so this means the matrix A minus lambda I is singular. Is singular. Okay, this is the equivalent. Okay, V is in the null space of A lambda I, tells us that V is an eigenvalue of A with eigenvalue lambda. So this is equivalent for non-zero vector V. Okay, so if we have a singular matrix, this tells us that the determinant of A minus lambda is zero. Okay. Now, this you can go backwards. If determinant is zero, then we have a singular matrix. For singular matrix, then we have the null space. Okay, the null space, then we can get non-trivial thing in the null space, non-trivial vector in the null space. Then we get an eigenvector. Okay, then we get an eigenvector. So this actually is equivalent. So to find the eigenvalue and eigenvector, so it suffices to find for what lambda, that is the eigen, so for what lambda, the determinant of this matrix A minus lambda I is zero. Okay, so this gives us an algorithm to compute eigenvalues of a matrix. Okay, okay, maybe we compute one example. Quickly compute one example. Next time we will compute more example. Let's this A to B example. A to B -4, -5, 2, 3. So A minus lambda I. This will be -4 minus lambda, 3 minus lambda. On the 5, -5 here, -2 here, 2 here. So the determinant of this matrix, we use this line means determinant, or you write a determinant. Then by 2x2 definition, 2x2 determinant minus -5 times 2. So you rearrange this, you get a quadratic. Okay, this is algebra, so we can skip that. So lambda plus lambda minus 2. So this you get a lambda minus 1, lambda plus 2. So we get a 2 eigenvalues. Okay, so we can let this thing to be 0. So we get lambda equal to 1 or lambda equal to -2. Okay, then you see if lambda equal to 1. Okay, if lambda equal to 1, then we see A minus lambda I. This will be A minus I, and this you write down this -5, -5, 2, 2. Okay, and you find the null space. Okay, we already know how to solve a null space. Okay, so you find its null space. Then you find its eigenvector should be, in this case, it should be 1, -1. Okay, 1, -1. Okay, now you can multiply any multiple. Okay, here x1 in R, x1 is not 0. Remember, eigenvector should be non-zero. Okay, now you find if lambda equal to 2, lambda equal to -2, then you find the eigen thing should be x1 times 1 negative this thing. Okay, this you solve in this thing. Once you find lambda, then you find the null space. Okay, the null space you can use linear elimination. Okay, use linear elimination to find. That's very easy. Okay, x1 in R, x1 is non-zero, etc. Okay, then we're done for this. Okay, next time we will compute more examples of eigenvalues and eigenvectors. Okay, maybe it's good time to stop here for today.